In this talk we will talk about Pareto optimal control for natural and supernatural motions. In the field of character animation, the main goal is to come up with methods that allow us to create a wide range of agile and graceful motions for humans, animals, and even imaginary creatures. For this work in particular, we focus on bipedal motions. So, to create motions then, we can use a controller and a physics engine. The controller is in charge of computing control inputs, joint torques, and external forces in our case, and the physics engine is used to simulate the dynamics of the world the character lives in. In the past few years, there has been a large body of work on physics-based character animation. One approach is to track reference motions. Online or offline optimization can also be performed using a seed input controller or some other form of input to achieve a controller which satisfies a desired objective. Often we need to adjust a learned skill to different requirements, as can be seen here from this example. The athlete here seems to almost effortlessly traverse the array of hurdles of increasing heights. Often in computer animation, the character is required to perform such variation of tasks as well. We take motivation from examples such as these to learn a set of controllers for achieving a range of task achievement. Let's look at the example of standing jump we use in the paper to describe the concept of Pareto optimality. On the x-axis, we show the peak height attained by the controller, and on the y-axis, we show the internal and supernatural energy used by the controller. Let the green region denote the space of all feasible controllers. This green region denotes a set of controllers for varying heights versus their internal energy usage. The red region represents unfeasible controllers. The set of controllers on the boundary of the green region, shown by the blue curve here, are Pareto optimal because given any controller on this front, an improvement cannot be made in any one dimension without making the other dimension worse. The Pareto optimal front of controllers is of interest because any controller on it represents an energy optimal controller for the respective height. In our framework, we try to achieve both natural and supernatural jumps. We realize supernatural forces by applying external forces on an as-needed basis. Hence, we penalize external force application with a large weight in our objective function. Jack Wang's work on optimizing walking controllers and Still and Chorus's work on developing parameterized jumping gates for a quadruped have looked into using multiple single objective optimization for developing a parameterization of running or walking and jumping skills respectively. We build upon these works by introducing a multi-objective optimization strategy to develop similar energy optimization parameterizations with the hope of efficiency and Pareto optimal front quality improvements. CMA has been found to be an effective optimization strategy for optimizing controllers for physics-based character motions. Covariance matrix adaptation is performed with each generation for the optimization until convergence. The derivative-free nature of the optimization and the covariance update make it particularly suitable for optimizing in the highly constrained parameter spaces often seen in physics-based character animation. Usually, single objective optimization combines various objectives as a weighted sum. In our single objective setup, the objective function comprises of three terms: the height constraint, the landing constraint, and the energy term, which measures the internal energy usage and reliance on external forces in case of supernatural motions. We perform a weighted sum of joint torques to compute the internal energy usage. The weights are empirically determined and intuitively represent how hard it is to move a particular joint. Supernatural motions are simulated by modifying the gravity of the world which is the same as applying a vertical force to all bodies. This is only done during takeoff to produce supernatural motions, which still look plausible. In the left plot, we show how the gravity varies with time during the course of a jump, while on the right plot we show the effect of this on the center of mass velocity during the course of the jump. The supernatural motion effort is measured by summing up the effective external forces over the course of the jump. We will plot peak height attained versus the energy term for all our examples. To obtain a parameterized family of energy optimal controllers, multiple single objective optimizations with varying objectives are performed. We start with the red input controller and the blue bins which act successively to bin the height objective for each successive optimization. An energy optimal controller within the current bin is used as an input controller for optimizing for the energy optimal controller which lies in the next successive bin. We get a distribution of natural and supernatural jumps as shown here in the graph. However, since the constraint satisfaction is realized by a highly weighted objective term in the same objective function as the penalty for reliance on external forces, the weight of the supernatural term cannot be increased arbitrarily. Hence, the optimization fails to discover the completely natural jumps, even in regions where peak jump height attainment is possible without help from external forces. We now describe our multi-objective optimization framework. For example of standing jump controller, we provide a constraint for maximum height of the character by specifying a sphere constraint of radius 0.2 meter, center at 3.5 meters. This constrains the peak height attained by the character. The spread along the height axis is created by violation of the height constraint in the objective function values. We plot just the heights on the graph rather than the objective function values. The energy axis measures the internal energy usage and the reliance on external forces in case of supernatural motions. There has been quite some work in the field of multi-objective optimization in the recent few years. Shown here is just a sample of the same. Multi-objective CMA extends the single-objective CMA to a multi-objective framework. The second work here shown is a real-coded non-dominated sorting genetic algorithm which uses crowding distance for selection as opposed to hypervolume contribution of the MO CMA. It uses real-value genetic operators, namely polynomial mutation and simulated binary crossover. The third work shown here, NSDE, is also invariant to rotation and scaling of the search space, just like the MO CMA. However, the hypervolume contribution of MO CMA has been shown to outperform them over some benchmark functions because of the selection strategy and also because of the invariance properties of the mutation and the CMA adaptation. As can be seen from this graph, after applying the MO CMA technique out of the box, we don't get a uniformly sampled Pareto optimal front across both natural and supernatural regions due to our problem setup. The natural regions on an average has less than 2 controllers, whereas most of the Pareto optimal samples tend to form in the supernatural regions. This occurs due to their hypervolume contribution as explained later in this talk. Also, the maximum peak height across the controllers does not satisfy the peak height constraint. We propose some modification to this framework to produce a uniform Pareto optimal front spanning both natural and supernatural regimes. Let's look at each component of the multi-objective framework in turn. Given a sampling of the objective function space, non-dominated sorting sorts the samples using the concept of non-dominance as defined in the paper. The highlighted points are the non-dominated samples in the provided set. Given a set of non-dominated points, we still need to sample them uniformly to create a Pareto optimal front of the required size. We choose a reference point in the objective function space, which is worse off than all samples. It is easy to come up with a point such as this beforehand. We then compute the hypervolume encompassed by the hypercube defined by this reference point and each of the non-dominated samples. The hypervolumes in case of 2D space is just the area of the rectangles shown here. However, the sorting can also be performed in n-dimensional function spaces. The green rectangles indicate the hypervolume contribution of each of the non-dominated samples. We sort all the samples using their hypervolume contribution and choose the first m samples required for optimization, where m is the required size of the Pareto optimal front. Let's look at a simple synthetic example to understand how the optimization proceeds given an input controller, as denoted by the red circle here. We will optimize for a Pareto optimal front of size 5 in this example, hence we sample 5 points. A non-dominated sorting is then performed. Since the number of non-dominated points is less than the Pareto optimal front size, we can keep all 3 in the front. These 3 points become the parents for the next generation, and each of them is sampled again. There will be some duplicates in the parents because of having 3 points rather than 5 in the parents. Again, these points are sampled, and since the size of the non-dominated points is the same as the Pareto optimal front size, we can keep all of them. We proceed to the next generation. Here, after sampling each of the parents and performing a non-dominated sort, the number of samples is more than the required size of the Pareto optimal front. Hence, a hypervolume sort is performed, and the best 5 are chosen to be the parents for the next generation. This process is repeated until the Pareto optimal front can no longer be improved. The energy axis here shown has been log scaled to make the graphs compatible to the other plots in this presentation. Using the BSOO algorithm out of the box doesn't give us a uniform spanning front across natural and supernatural regimes as shown earlier. Also, the optimization converges on an average before being able to reach the maximum height of the jump specified by the constraint. By resampling the failures at a pre-specified rate, we get better convergence of the jump heights, but the natural region and the supernatural region still don't get uniformly spanned. This happens because the hypervolume contribution of each point in the natural region is much smaller than the hypervolume contribution in the supernatural region. This is because of the high weights associated with them in the objective function space. Let's look at another run of the same setup as before, but this time plotted on a linear energy scale. Here, it is more clear that the hypervolume contribution of any points in the natural region is going to be much less than any point in the supernatural region. We perform a log scaling of the objective function space, which results in hypervolume contributions across natural and supernatural regions to be uniform, and hence we get a uniform sampling of both natural and supernatural regions. Also, we get a uniform spread of controllers covering the entire range of possible heights. Here we show a run of samples generated from our RMO algorithm. Let's look at some results. Shown here are some of the controllers from the Pareto optimal front, ranging from a natural low jump, a natural high jump, a supernatural intermediate high jump, and a supernatural high jump. Here we show all the 16 controllers on the Pareto optimal front. The brown characters represent natural motions, whereas the blue character represents supernatural motions. Due to the controller representation, the takeoff of the jump looks slightly unnatural, More work is required in the effort metric to make the jumps look more natural. We have only tested the multi-objective optimization for 2D objective function spaces. We hope that most of the algorithm should scale to higher dimension, but some modifications to sampling might be required to avoid incurring huge computation costs. We built a discrete sampling of the Pareto optimal front. Ideally, a continuous Pareto optimal front should be recovered. Efficient Pareto optimization of higher dimensional objective function spaces is left as future work. The resampling process can be made more intelligent rather than using a pre-specified rate as in the paper. Application to different tasks can also be explored. At this point, I would like to thank you for your attention and would be happy to take any questions. Thank you.